All right, today we are going to do some reviewing over factoring. Factoring we did in Algebra 1, but we're going to take a look at a little bit more difficult cases, but try to get some reviewing done of just some factoring. Okay, so we're going to talk about common factors, greatest common factors. We're going to talk about factoring into binomial factors. And we're going to take a look at some special quadratic expressions that we can factor very quickly if we can recognize when they pop up. Okay, so first things first, why do we call it factoring? Why is this called factoring? Well, what we're trying to do is we're trying to take something and break it down into what we call factors. Factors are two terms or two numbers multiplied together to give us back the original. So if I wanted to factor 12, we know this, right? Factor 12, you can factor it into what? 4 and 3 seems to be the most popular response to that, so we'll use that. And there's two factors. It's interesting that we have to list two of them because it takes two numbers to multiply together to give you 12. You can't say that I'm going to factor 12 into 4. It doesn't make any sense. Okay? Now, of your factors of 12, 4 and 3, can you factor either one of those two? The answer to that is yeah, we can factor 4 down into 2 and 2. That's what we call factor completely, right? We want to make sure that we factor all the way down into prime factors. So sometimes it takes a couple of rounds of factoring. Now, that's something that we're going to take a look at in the near future. Not so much today, but in the near future. Okay? So sometimes we want to just keep factoring. Now, same thing with polynomials, right? That's a pretty easy case of factoring when you just have a constant, a number. But when we're trying to factor polynomials, it's the same thing. We're trying to break that polynomial up into smaller polynomials that when you multiply them will give you the original bigger polynomial. Okay? So, let's take a look. For example, this. Right? This is a polynomial, it's a trinomial. 3 terms, and we want to start factoring it. We want to start breaking it up into smaller polynomials that will multiply together to give us this guy, right? And usually students remember that first thing you always look for is a greatest common factor. So we look through these 3 terms. We need to come up with something that will divide into all coefficients. And if they have x's in common, then we can factor those out as well. If we look, we can divide all of these guys by 3. So 3 is going to be part of our greatest common factor. They all have x's, they're all x terms. And so we want to take the fewest number that they all have in common. This guy only has one x, x to the first, so x to the first is going to be the part of the greatest common factor. So I'm going to put this down here as well. Now, factors, we need 2 of them. We need 3x times something that will give us back 9x cubed plus 30x squared plus 21x. Now, just like a long time ago, when you were taught to factor, you were trying to factor 12, and you would say, okay, well, I know 4 is a factor, but I can't remember the other one. What would you do to find the other factor? Well, you would simply divide 12 by 4 and get 3. Same thing here. I know that 3x is a factor. I don't know what the other factor is that I have to multiply to it. So what I'm going to do is I'm going to divide everything by 3x. So 9 divided by 3 is 3, x cubed divided by x is x squared, 30 divided by 3 is 10, x squared divided by x is x, and then 21 divided by 3 is 7, x divided by x is 1, and so 7 times 1 is 7, we don't bring it down. Okay? So that's how we come up with the other polynomial. Okay? Now, we would want to try to factor this trinomial down. And if we can factor this trinomial down, it will factor into a smaller polynomial, which is going to end up being 2 binomials, if you remember this from Algebra 1. Now, in order to remember how to factor a trinomial, I'm going to come over here and do a side problem. What if I asked you to multiply 3x plus 7 and x plus 1? Right? Do you remember doing that? We would FOIL, right? Double distribute. Distribute here, and then distribute the 7. Now FOIL says we're going to take the firsts. 3x times x would give you 3x squared. Now take a look at this. 3x squared here and here. So what that means is these first terms need to multiply to 3x squared. So why don't we turn around and go the other way, and instead of trying to multiply 3x and x, why don't we factor 3x squared? We'll factor 3 into 3 and 1, and you factor x squared into x and x. X times x will give you x squared. And that's how we would come up with the 3x and the x on the right-hand side over there. Right? Now, if you continue to FOIL, F-O-I-L, right? I know I'm going to skip ahead a little bit, but if you multiplied the last terms, you would get plus 7. And that happens to be the last term over here. So your two last terms in your binomials need to multiply to give you 7. Okay, that's great. It's 7 and 1. Or don't forget that negative 7 and negative 1 can also multiply together to give you positive 7. So which of those two sets are we supposed to use? Well, that's where the O and the I in FOIL comes into play. The outs and the ins, here and here. If I multiply 3x times 1, you get 3x. Multiply 7 times x, you get 7x. Now these two middle guys end up being like terms that we would add together to get 3x squared plus 10x plus 7. So what we're really looking for is we're looking for factors of the first term and the last term that will multiply together and add to the middle term. So it turns out that plus 7 and plus 1 are those factors. So I would take the factors of the 3 and 1, multiply it into the factor pairs of 7 and 1, negative 7 and negative 1, and then add them together and use the ones that added to 10. So we got to multiply the 7 times 1 and the 1 times 3. So to place these guys correctly, we've got to link the factors that we're supposed to be multiplying together. We're supposed to be multiplying the 3x times 1 and the 1x times 7. And so that's where we'd place the 7 and the 1. Now, the right-hand side here is just designed to show you where these things are coming from. I don't want this to confuse you too much. But we're basically working backwards to get to those two binomials that I just came up with. All right? That's the why in the process. Let's go a little bit quicker and just get to the how. Okay? Next one. Still looking for a GCF. Still want a greatest common factor. One thing that we have not seen before in Algebra 1 was if this lead coefficient was was a negative. Now we can look at these three coefficients, the two coefficients in the constant, and see that they're all divisible by 2. They don't all have x's in common, so we're not going to take any x's with the GCF. But because that lead coefficient is negative, I want to make sure that I factor out a negative 2. That way when I divide through by negative 2, the first coefficient will turn positive. I always want him to be a positive. So negative 6 divided by negative 2 is 3x squared. 16 divided by negative 2 is negative 8x. 32 divided by, that's supposed to be a negative 2, is negative 16. Okay? Now, I want to try to factor down this trinomial into two binomials. Again, these first terms, if I were to FOIL when I had the binomials, these first two terms have to multiply to 3x squared. So factor down 3 into 3 and 1, x squared into x and x. I'm going to bring those factors over here. I'm going to factor down 3, and then the last terms have to multiply to negative 16. So I need factors of negative 16. So 3 and 1 are my factors for 3. Negative 16 have several factor pairs. Negative 16 and 1, negative 4 and 4, negative 8 and 2. Or we can go 16 and negative 1. Well, negative 4 and 4 is the same. 8 and negative 2. I need to go through and come up with a multiplication set that will add to negative 8. And what you do here is you just start trying them. There's no other way to do this other than to just start multiplying some numbers together and see which ones will add up to negative 8. So I could do 3 times 16. 3 times 16 is negative 48. That's going to end up being way too big, so I'm not going to use that. You could flip it around and go negative 16 times 1, which is negative 16. 3 times 1, which is 3. Add those, you get negative 13. Still not what we need. So move on. How about 3 times negative 4, which is negative 12. 1 times 4, which is positive 4. Negative 12 plus positive 4 is negative 8. Hey, that's it. That's it. We need it to be negative 8. So I've got to multiply the 3x times negative 4 and the 1x times positive 4. That's where these smiles come into play. You link those, the 3x times the negative 4, the 1x times the positive 4. And there we're done. Now luckily it was the second set that I tried, but sometimes it's not, and sometimes it's going to be the last set that you try. So the point is just keep trying until you get the combination that you need. If you go through all the sets and you're very confident that you did it right, and you still can't figure out how to make this work, it is entirely possible that this trinomial is already prime and can't be factored. It's possible. Doesn't happen very often, but it can happen. So just know that you might end up checking all of the factors and not come up with anything because the trinomial is prime. Okay? But the real point is just continue to try, okay, until you find what you need. All right? Next one. Looks a little bit like the last one, which is why I backed up for a second. Greatest common factor. Look at this. The greatest common factor is just a negative 1, right? You can't divide anything else into 6, 17, and 5 except for 1, but I still want to take the negative to make that lead coefficient positive. If I divide everything but through by negative 1, you get 6x squared plus 17x plus 5. And now this trinomial, we want to try to factor down into 2 binomials. Now, I don't know. The lead coefficient is not so easy to factor anymore. I've got to factor 6, and I've got to factor negative 5. Now, I do know that x squared is going to factor into x and x, so I can go ahead and put those down here if I want. But I don't want to write in the factors of 6 just yet until I know exactly which ones I'm trying to use. Now, the next thing I want to tell you is that that lead coefficient is a positive 6. I only want to use positive factors. Don't ever try to use a negative factor for those. All right, the negative 5 could factor into negative 5 and 1 or 5 and negative 1. And I need a combination of those guys that will multiply and then add to negative 17. So, we just start trying. 6 times negative 5 is negative 30. 1 times 1 is 1. That's going to be way too much. So flip it around. 6 times 1 is 6. 1 times negative 5 is negative 5. You add those, you get positive 1. Not what we need. So try. 6 times 5 is 30. 1 times negative 1 is negative 1. Add those, you get 29. Too much. 1 times 5 is 5. 6 times negative 1 is negative 6. You add those, you get negative 5. Not what we need. So now we flip over to the 3 and the 2. 3 times negative 5 is negative 15. 2 times 1 is 2. And I'm going to stop and realize that I messed up. We're not trying to factor negative 5. We're trying to factor positive 5. I messed up. This should be a positive 5. After we divide out the negative 1, we get a positive 5. So our factors are going to change here. So, okay, my fault. Sorry. 5 and 1, negative 5 and negative 1. We do want to use the 2 negatives possibly to get a positive 5. Okay? All right. So if we're to check, we could do 6 times 5 and 1 times 1 and add them. That's not going to be the right one. We could do 1 times 5 and 6 times 1 and add them. That's not going to give us what we need. And we can go through the 6 and the 1 and the negative 5 and the negative 1, and that's not going to work either. So we keep checking and keep checking and keep checking. 3 times 5, 2 times 1, they don't add to what we need. If we come down and do 3 times negative 5 and 2 times negative 1, we get negative 15 and negative 2, and when they add, you get negative 17. So that's what we need. I'm going to use 3 and 2 as my factors for 6 then, and I'm going to link the 3 to negative 5 and the 2 to negative 1. And that's how we're going to factor this. Okay? We would want to look inside the parentheses to see if those parentheses would continue to factor, just like we did up here. Okay? But these guys aren't going to, because these are x to the firsts. Those lead terms are x to the firsts, and so they're not going to lend itself to factoring anymore. All right? So we're done right there. Making some sense? All right. This guy. Tough part might be the greatest common factor. 6, 17, and negative 3. We can't divide anything into all three of those. But they do have x to the third in common. They all have at least 3 x's. So I can factor out an x to the third. And when we do, if we divide everything by x to the third, we should get 6x squared plus 17x minus 3. Okay? Now factor that trinomial into 2 binomials. Try to factor 6 and negative 3. So 6 can factor into 6 and 1, 3 and 2. Negative 3 into negative 3 and 1, 3 and negative 1. All right, I need a combination that's going to add to positive 17. So I just try. 6 times negative 3 is negative 18. 1 times 1 is 1. Negative 18 plus 1 is negative 17. It's close. It's just negative instead of positive. So that tells me that I have the right pairs. They're just the signs are off. So we actually want to go 6 times 3 and 1 times negative 1. 6 times 3 is 18. 1 times negative 1 is negative 1. So I'm going to use 6x and 1x for my factors of the first term. And I'm going to use 3 and negative 1 as factors of negative 3, but I have to link them correctly. The 6 goes to the positive 3. The 1x goes to the negative 1, and so that's how they need to go into the parentheses. And there we're done. Okay? Hopefully you're finding this easy and all the memories of factoring from Algebra 1 are flooding back. If not, do make sure you come in here and get as much help as you possibly need. Okay? All right. Next guy. Next guy introduces us to one of those special cases I was talking about at the beginning. Right? We're still going to look for a GCF. So greatest common factor. We're going to be able to factor a 5 into both of those, and they each have at least 1x. So I'm going to divide both of these terms by 5 and get 25 divided by x, then we get x squared. 45 divided by 5 is 9, and x divided by x is 1. And so 9 times 1 is 9, so we get 25x squared minus 9. Now, if we were to factor this, and we look inside the parentheses and we see that we have a quadratic, right? We have an exponent on our x that's bigger than 1. So we might be able to factor this. So normally we'd go through our process, right? We want to factor down 25. Well, x squared is going to factor into x and x, no problem. Factor down 25 and factor down negative 9. Well, factors of 25 are 25 and 1, 5 and 5. Factors of negative 9 are negative 9 and 1, negative 3 and 3, or 9 and negative 1. Now, there's not a middle term. Did you notice that? We don't have an x to the first term. That's usually sitting right here. Which means that now we're talking about 0, right? It must be 0. That's why we don't write it if it's a 0. So we are looking for our factor pairs that will multiply together and then add to 0. Well, obviously 25 times 9 and 1 times 1 is not going to do that. 25 times negative 9 and 1 times 1 is not going to do that. If you go through all of your checks, what you would find is that 5 times negative 3 is negative 15. 5 times 3 is positive 15, and those will add to 0. So our factors of 25 that we're going to use are 5 and 5. Our factors of negative 9 that we're going to use are negative 3 and negative 3. And we can put those anywhere just because our factors of 25 that we're using are the same, 5 and 5. Okay? And so we're done factoring the exact same way we've been factoring. But I want you to notice something else. What's the square root of 25? Well, it's 5, right? What's the square root of 9? Well, it's 3, right? The square root of 25 and 9 are 5 and 3, and those are the numbers that we use in our binomials. There is a trick to this. So it only works for what's called a difference of two squares. This is a difference of two squares. It's called a difference because there's a minus sign. It's two squares because there's two terms. And squares because 25 and 9 are perfect squares. And so is x squared for that matter. This only works if you have a difference of two perfect squares. If you have that, then all you have to do is you square root each term, put those results in our two sets of parentheses, and because the middle term is 0, they have to add to 0, we just flip-flop signs, plus and minus. Okay? So, hopefully I'll make it make more sense in this next one. We want to factor out a GCF. So we're going to factor out a 2y. 2 will go into 8 and 18. They both have a y, so we factor out a y. When you divide both these guys by 2y, what you're left with is 4x squared minus 9. Now, two terms. That's my red flag. That's my trigger to go look for my trick. Two terms and a minus sign means we have a difference of 2. And I want to make sure that the 2 that are in here are perfect squares. The square root of 4 is 2. The square root of 9 is 3. The square root of x squared is x. So I can square root everybody. That means I come down here with my two sets of parentheses. I square root 4x squared and get 2x. And I put that here and here. I square root 9 and get 3. I put that here and here. And because they have to add to 0, the middle term is 0, we go plus or minus. And then we're done. Okay? That's it. This is a little bit easier, right? But it has to fit. You do not get to factor this way very often. This is a gift. This is a treat when this happens. So don't try to do this all the time. You can only do it when it fits the difference of two squares. Okay? Next guy. Look at this, and you can see that we have a GCF of a negative x to the fifth. That lead coefficient is a negative 1, so I want to take a negative 1 with the x to the fifth. They have 5 x's in common. If you were to divide both of those two terms by negative x to the fifth, you'd get x squared minus 16. And inside the parentheses, since this is bigger than just an x to the first term, I would try to factor. I've got two terms and a difference. That means, can I square root these two? The square root of x squared is x. The square root of 16 is 4. I certainly can. I create my two binomials and go x, 4, and plus or minus so that those smiles would add to 0. And we're done. Okay? Hopefully this is been a pretty good memory jog for you, and you're ready to rock and roll. So go ahead and get into the homework. It's out in Canvas. Have that done by next time, and we'll go through any questions you have.